Well, I am really excited about this module because this module is going to radically expand your notions of what's possible using both automated technology for software engineering, and it's just going to increase your ability to collaborate with others in software development to an unimaginable degree. Or at least it's unimaginable if you've never used build technology before. So we're actually going to have to spend a fair amount of time on build systems and techniques, and it's going to span a couple different modules. And it's really going to pervade most of the rest of the semester, but I think it's just going to fundamentally change everything for you, and I'm very excited to present this material to you. So let's start talking about build technology. The objectives of this module is to first just understand why it is the case that build systems have evolved. And they've been around for a very long time, and the original developer of the Make system, which was the first build system, has won very prestigious software engineering awards based upon the fact of kind of coming up with this idea of a build system that was kind of separate from any particular software system, but could be kind of a unifying technology and set of principles for building any software system at all. It's, really it was a conceptual leap in software engineering when Make came out. Because if you don't have a system like Make, it turns out that enabling multiple people to build a system, or enabling people to build lots and lots of different systems and install them, turns out to be a very complicated and difficult task if you don't have some kind of build technology. And so I want you to come out of this really kind of aware that no self-respecting software engineer would ever create a system of any complexity and expect anybody else to use it without having some sort of build system to help others automate the processes of doing compilation testing and so forth. Thus far in the semester, you haven't been able to do that, and I assume that it's led to problems when you've tried to share your projects with other people. So, and I want you to be kind of passingly familiar with some of the different build technologies that are out there, but we'll go into one in detail, which is called Ant. And I'm gonna actually provide you with a kind of a framework for a build system package written using Ant that I've been using in this class for a number of years with success. I've also been using it in my own software development for a number of years, so it's pretty well tested, although certain bugs may remain. Okay, so here's the deal. Modern software development, we've got lots of different developers, we've got lots of different platforms, we've got lots of different types of users. We want things to run on, Windows machines, Linux machines, of all different flavors. People might even be using different versions of Java or other programming languages installed in different places. Depending upon the user, you might want to have a binary distribution for certain types of people, a source level distribution for other types of people. There might be plugins. Developers may want to use different kinds of IDEs. In our class, we don't allow that because for pedagogical reasons, I think that the learning curve is accelerated if you can all work together and have a common framework. But in the big bad world, someone who's really attached to Emacs or Xcode or whatever isn't going to give it up just because you think that your own preferred environment is better. So what you really want is the ability for people to all use their preferred environment, yet be able to cooperate together. And that's pretty difficult, okay? And that is not a Java problem, that's just a software development problem. So what we want is some kind of framework which is basically independent of the IDE, is independent in some sense of the platform. It may have to build in intelligence about the difference between different platforms to do its job, and it probably should, but it abstracts away the details of the particular platform, and it allows developers to build the system. And when I say build, I mean things like compiling, executing, running tests, running quality assurance, building distributions for further distribution, packaging it in various ways, and so forth. And this should all be automated. Okay, it should basically something that could be run from a script or in a single command line or whatever. And if you can do this, then the velocity of development will go up by a great amount. Okay, and your good developers will be much happier, and your weaker developers will be will also be happier. Okay, because they're not going to get, you're not going to trip over certain low-level things that the build system can do for them. So in our class, what we're going to do is we're going to create a build system and use a build system that's based upon Ant, and a dependency manager called Ivy, and a set of standards for how we're going to structure our build files and so forth. But before we get to our specific solution, just want to quickly make sure that you're aware that there's other things out there. The granddaddy of them all is GNU Make, and this is kind of a Unix-based system primarily for compiling C files. Syntax is a little problematic because tabs are significant in these files, so that's having non-printing characters be important is always a problem. But anyway, it was a phenomenal breakthrough. It introduced kind of dependent targets and a lot of the different kinds of concepts for build systems that survive to today. If you're doing C programming, then this is generally the system that's used to build those kind of systems, and so you'll need to get to know it. We won't be talking about it in this class, but it's important to know that it exists. So some of the things that it introduced is the idea of dependency analysis. So for example, if you've got a large system and you have to compile various things and create executables, it will do checking of timestamps to only recompile the things that need to be recompiled when you make changes, and that of course is a tremendous time saver. And there's a bunch of iMake, CMake, SCONs that are all kind of related to the make build system. System we'll be using in this class is called Ant. Ant was basically originated as a hack when the Tomcat web container was being developed. They needed some kind of build system. They didn't want to use Make for it, so they started hacking together some Java code, and eventually it kind of split off into its own separate project, and it retains certain things in common with Make, this idea of having dependent tasks and timestamp checking to minimize the amount of rework required when you redo things. It is different from Make in that it uses XML as its language, and it's not tied to kind of a shell environment. Instead, it runs inside a Java process, which has its own kind of strengths and weaknesses. And if you're doing Java development, Ant is the de facto standard for building. I would still say that's true, although there's another system called Maven, which we'll talk about a little bit, that's becoming more and more popular. Yeah, all those things. Okay, so Ant versus Make. Basically, it comes down to Make is still more popular, supports any programming language, operates within a shell environment, and can basically, anything you can do in a shell is easy to transfer into a Make environment. Ant has a lot of specialized capabilities for doing Java development. In particular, it tries to be, it has a certain amount of stuff that's for C or other programming languages, but really Ant is pretty much for Java. And if you're doing Java development, you're either going to pick Ant or Maven. And then, there's other, if you're doing Ruby development, there's Rake and so forth. So there are some other languages or other build systems out here. The contender for being the kind of the successor to Ant as the build platform of choice is Maven. I think it's almost there with version 3. And the idea was that it wanted to take the kind of abstraction up to another level higher than Ant. So it built in dependency management. And to be frank, the first couple times they didn't get it right, in my humble opinion. And it was just kind of I mean, people either loved Maven or hated Maven. The problem with it was that it really was a black box, and if it didn't do exactly what you wanted it to do, and you weren't content with kind of the Maven way about how your whole system should be structured, then you were in trouble. Okay, nowadays it's getting better and better and better, and probably in the next year or two I'll switch over to teaching Maven, but I still don't feel like it's quite there yet. And even if you do learn Maven, you still need to know Ant, because the amount of projects that are built using Ant far exceeds those that, as far as I can tell, that have been built during Maven, just because Ant is 10 years older than Maven. So it's very important if you're dealing with projects that you understand Ant, and Maven is once you understand Ant, is basically pretty easy to get your head around, but it just hides a lot more. Okay. The big thing with Maven is that, unlike Ant, it gets a lot of its power from the idea that it says, listen, we want to lay out projects in a certain kind of way. We want certain kind of operations to be available. And so you should just follow these conventions, and then things will be very simple. And I think their conventions are, for the most part, actually quite reasonable. So I don't really argue with that part. The second thing that they do, which was a real breakthrough, was this idea of dependency management, so that if you needed third-party libraries, Maven had a mechanism for downloading those libraries automatically off the net, and then if those libraries needed other libraries, it would in turn get those libraries off the net. So you had this way of kind of recursively and transitively satisfying all the dependencies. And in the olden days, it did a really bad, well, in certain cases it could lead to immense amount of files being downloaded, and the whole dependency management thing, it wasn't exactly Maven's fault. It was the fact that the community was still trying to work out how exactly dependency management should be done. And I think that it's closer and closer to being the right way to do things. Now, the Ivy tool is a add-in to Ant, okay, that provides just the dependency management component. So, and it arose in response to some of the failures of Maven in terms of just its conceptual model of dependency management. And also the fact that Maven basically tries in one black box to do kind of everything. And the Ivy guys said, listen, dependency management is an interesting problem in its own right. Let's solve that problem well. And then anybody that needs just dependency management can get it. They don't have to get everything else that Maven comes along, that Maven introduces, if all they want is the dependency management component. So as a result, if you have Ant plus Ivy, you get something that offers most of the goodness of Maven. It's a little bit simpler to understand. It's a little more exposed, so there's a little less black boxiness to it, which can be either a plus or a minus. And the representations of dependencies are in general a little better than what Maven supports, just because Ivy does a better job of it. So, I think that the major controversy in the community is, between the people who say Maven, 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 and there are a lot of people like that, versus the people who say, I don't really like Maven, but you give me Ant plus Ivy, and I can do everything that I want to do with Maven, and I can do it the way that I want to do it. So for the moment, I'm still really kind of coming down on the side of Ant plus Ivy. I feel like that's a better thing for you guys to be exposed to, in that you have a you learn the language of and dependent and build systems, okay, at a level that is less exposed in Maven. And then if in turn, since Maven is kind of built on top of Ant, if you want to move to Maven in the future, it's not that big a deal. Okay, so that's my conclusion about those two things. So what we're going to do is we're going to use Ant plus Ivy, and we're going to use a specific kind of template file, set of template files for Ant and Ivy that will make it very easy for you to get going quickly with building the systems that you want to build. And then as you it has a lot of code that shows how you do various things, the common operations in Ant and Ivy, that will enable you, as time goes on and you want to kind of customize it to serve your own purposes. It should be relatively straightforward to do it. Okay, so how does Ant work? Ant is a software program that reads in a file called build.xml by default, and that file contains a bunch of targets, which are little pieces of code. And there might be a target for compiling your system, a target for running JUnit on your system, a target for generating the JavaDocs for your system, and so forth. And then in order to implement those particular targets, you invoke a set of Ant tasks. Okay, so there's a copy task, there's a compile task, there's a delete task, there's a JavaDoc task, there's a JUnit task, and so forth. And then you hook these targets together by the specification of dependencies. And so if before you run JavaDoc, you want to make sure that the system compiles, you can make JavaDoc depend upon the JavaDoc target depend upon the compile target, and then when you run JavaDoc, Ant will ensure that the compile target is satisfied before it goes off and do targets. Similarly, if you want to make sure that the system compiles before you run tests, you can make the JUnit target also depend upon the compile target, and then those dependencies will be satisfied. Okay, so let's say that you wanted to run the JavaDoc, and you want to run JavaDoc and JUnit. Okay, you can say that you want to run JavaDoc and JUnit. You can make each of them depend upon the compile target, and the compile target will only be invoked once. So Ant will automatically kind of figure out what are the common dependencies and order everything in such a way that targets only have to be executed once. So again, it kind of minimizes makes the entire build process more efficient. Okay, so here's an example of an Ant target. It's got this kind of XML syntax where it's the element is called target, and you can pass various you have various attributes specified for that particular element, and then you can have these internal tasks like this JavaC. You can have an internal element of the target element, speaking in XML terms, which is a task, speaking in Ant terms, that invokes this JavaC, the implementation of the JavaC task in Ant. Okay, and hopefully this is pretty self-explanatory. The target is called compile. It depends upon some other target called init, which might create directories or clean things, or who knows what. We've got a little documentation string for this target, and then this target, the compile target, has exactly one task that implements it, and that task is called JavaC. And you specify a source directory, and you specify it by this kind of crazy syntactic, metasyntactic character here that we can talk about, this $, curly brace, and a destination dir, which also has a little bit of special syntax inside. And so you can kind of guess that looking at this, that what we're going to do is there's some source directory which is defined somehow. We don't know how, but it is. And we're going to compile all the files in our source directory, and the output of it is going to be put into the this classes directory. Okay, And before we do this particular target, we're going to invoke the init target. So that's, that's the build system in a nutshell. Okay, pretty simple, straightforward, conceptually. The devil's always in the details, so it turns out that there's a lot of kind of little things you have to understand to really make things work the way you want them to. So so Ant, I think, as a language, is a pretty good, it's a pretty good approach. It's become very popular. It has a certain, kind of maximal abstraction level, which Maven set out to solve by implementing kind of a new language, which would be implemented in terms of Ant. But Ant is really a language, and just like any language, it doesn't really specify how you use it. And so what I'm done for this class is create a kind of set of practices for using Ant, along with a lot of template code that helps you get going quickly and enables you to use a fairly powerful and expressive build system without a lot of work on your own, evolving from zero a system that can satisfy your needs. We built pretty big projects, 100,000 lines of code, 200,000 line of code systems with this build system. So it's we've demonstrated that it's useful in practice. But you're not going to build a system that big today, okay? What you're going to build instead is a very small system called robocode-pmj-dacruzer, which builds a robocode robot called dacruzer, and the robot itself, I'm sorry to say, not very interesting. Okay, very lame in terms of its behavior, and that's okay because you're not going to really care about this robot. What you're actually interested in is the build system around it that enables you to easily share this code with other people and have them easily be able to compile it, test it, run it, document it, and so forth. It's also the basis for the integration of a bunch of other third-party tools that we'll be looking at over the remainder of this semester. One of them is called Checkstyle, one of them is called PMD, there's one called findbugs, and there's a bunch of other ones as well. And so we introduced the build system to give a framework for adding in these other tools without introducing a lot of overhead. And you'll see it's pretty sweet, this tool. It's going to download and install these tools automatically the first time you try to use them. And the build system is structured so that if you come up with some other third-party tool that you'd like to add in, that you can pretty easily kind of hook your additional build component into the existing framework. Later on, we'll be showing continuous integration mechanisms like Hudson or Jenkins, and this is well adapted for that role as well. And we're going to use Ivy, as I said before, to automate the downloading of these third-party libraries. Okay. So the way we do this thing is at the top level we'll have a build.xml because that's what Ant expects, but we'll also have a bunch of other star.build.xml files where the star is going to be a name that refers to the particular tool that we want to hook into our build system. So we may have a JUnit.build.xml, a Checkstyle.build.xml, a PMD.build.xml, and so forth. A whole bunch of those. Then we'll have a source directory where the source files are, a lib directory where Ivy is going to put the executables for any third-party libraries that are required by this system. And then we'll have a build directory where Ant is going to place any of the files that are generated through the various tasks that we invoke in the system. That's basically it in a nutshell. A lot of different build operations, compiling, creating jar files, running JUnit, doing JavaDocs, and so on and so on and so forth. Lots and lots of different ones. Normally, not in almost all cases, clean is not its own file, but for example, and compile is part of the build.xml. But on this side, for example, there's a checkstyle.build.xml, a findbugs.build.xml, a pmd.build.xml, and so forth. So the structure of this is intended to be to support modularity in the sense that if we just had one gymongous build.xml file, it'd be very hard to understand how the individual pieces work together. So almost all of the code associated with the JUnit, implementing JUnit with our build system, is going to be in the JUnit.build.xml file and the build.xml file, the combination of those two. By splitting things off this way, we do get a bunch of different files, but it also means that if there's a tool like Dependency Finder that a particular developer just never wants to use, then they don't really have to install that those libraries. They don't have to see code related to it. It's just one file that they can ignore, and so the overhead of you only have to understand the parts of the build system that you care about. And the coupling is very clear in this particular system because of the way we've split things up. And the coupling looks exactly like this. There's this build.xml, which is basically the project-specific definition. So here's you're going to define the name of your project and whatever third-party libraries that project uses directly. So for example, in the case of a robocode project, you're going to indicate in the build.xml file that you have to download the robocode system and get these robocode lib files in your compile path and so forth. And that build.xml depends upon another file called common.build.xml, which is just some utility code that shouldn't ever really have to change. And it's split out so that when you're reading the build.xml file, it's fairly small, okay? And you're not kind of having to wade through lots and lots of code that is can be viewed as a black box basically for your purposes. Then we have a bunch of other files, PMD, findbugs, dist, checkstyle, and so forth, that are all built on top of the build.xml file, and then in turn, of course, on top of common. And they take these definitions in build.xml and add in additional code that enables you to run the PMD tool, the findbugs tool, build a distribution, run the checkstyle tool, and so forth. So the point is that you could basically delete any of these files or add more files of this type, and you haven't really and because all of them simply depend upon the build.xml and not upon each other, these are all completely decoupled and independent from each other. So whereas there may be a lot of files, the actual structure of understanding any code is quite simple. Okay, if you want to understand Checkstyle, then you have to look at this file, and you have to look at this file, and you might have to look at this file, but that's it. No matter how many more files there are in the system, there's only really 3 files that you have to look at to understand any particular piece of the build system. Okay, so it turns out that, as I said before, the build.xml provides most of the project-specific stuff, although it turns out, unfortunately, in certain cases, there's a few other files that have some project-specific stuff. And it just turned out to be more complicated to try to get them all into build.xml than to have them spread out a little bit. So, and I will kind of show you that stuff as we go through. And then it turns out that as you actually try to invoke the build system, if you haven't updated these things correctly, you'll get failures, and it will be pretty obvious. Okay, and then as I said before, these other build systems, like Checkstyle.build.xml and so forth, they support a single tool, and they typically involve 3 different targets: a foo.tool, or a tool target, a report target, and just a basic high, top level invocation target. And you'll see that as we do the walkthrough of these. So, using this build system, generally the first thing you do after you download a package that's built this way is you just type ant, and it's going to go ahead and make sure that the system compiles, and it will download any other packages necessary to make sure that can happen. And I'll show you this in the accompanying kind of walkthrough lecture of how that works. So it's pretty simple, pretty black boxy. Okay, but of course you want to do more things. You want to do more than just be able to compile the system. You maybe want to run it or invoke various quality assurance tools on it and so forth. And so for these other kinds of behaviors, what you'll do is you'll invoke ant, but you'll specify the build file that you want invoked. Okay, and so for building the distribution of the system, we'll say ant -f and then the name of the build file that implements that particular command. Okay, so there's some good news about it. This kind of decoupled thing is that you have a single file for each particular kind of tool that you want to invoke, so there's not very much coupling and things are very modularized. The problem is that if you want to do a release and you want to make sure that JUnit is successful and PMD runs and Checkstyle runs and findbugs runs and none of them get any errors, then you're doing a lot of typing, okay, which doesn't seem appropriate given that the whole point of build tools is to have a kind of automation. So the way we fix that is we have yet another build.xml file called verify, and the idea of verify is it's a file that imports other important quality assurance tools and invokes them all in turn. So it will make sure that the system compiles, it'll make sure that it passes JUnit, make sure that PMD runs without error, Checkstyle, JavaDoc, findbugs, etc., etc., etc. Okay, so that adds. It turns out that this system, the verify file, actually violates our nice little decoupled abstraction that I showed you previously, because it's actually got to import a bunch of these other files. But the benefit of that now is that we can now very easily, we just type ant -f verify.build.xml and then go off and watch the characters scroll by on the screen as ant goes off and make sure that everything's perfect. And it's going to turn out that this is going to be the command that you're going to invoke, hopefully, multiple times a day. Every time you get an update of a system from one of your classmates, you'll just run this first thing in order to make sure that they didn't introduce any bugs, and so that you've got a clean system to start working on. Similarly, when you're about to share your changes and enhancements with somebody else, the last thing you'll do before sharing it is to run this to make sure that you haven't introduced inadvertently any bugs or problems. There's a lib directory, and as I mentioned before, and that is a directory that you'll never really touch. It will be automatically maintained by Ivy, and that's going to be the location where any third-party libraries needed by your project are going to be placed. Okay. And then, as I said before, also there's a build directory. That also, well, you'll go in there sometimes, but mainly you won't write any files there directly. That's the place. That's the directory where Ant will place things. Like they'll place all the .class files generated from compile. The HTML files generated by JavaDoc will go in a subdirectory of the build directory. The unit test results from JUnit will go in a subdirectory of the build directory, and so forth. Now I want to mention that by default, both Ant and Eclipse want to write into the build directory the class files. That can be kind of a problem in certain circumstances, and so it's really better that Ant and Eclipse stay out of each other's way when writing class files. And so the best thing to do is have Eclipse write to a different directory called bin rather than build, and you can set that in the project properties very easily. Now, what's going to happen when we get started with this, with having a build system, is that there's two kinds of ways you can test your system, conceptually speaking. The first way is through running unit tests that you've constructed yourself and using the JUnit framework. And that's good. And that's kind of tests the behavior of the system and make sure that it satisfies the specifications. On the other hand, there are now these new tools, Checkstyle, findbugs, PMD, etc., that can do an automated quality assurance, and that's going to basically look at the style and certain idiomatic, idioms that you use in your coding and make sure that they satisfy best practices. Now, when we create distributions using our build framework, we use a slightly different approach than what is normal. Often you'll see things like 5.1.0 as a release number, where the first number is a major release number, the second number is a minor release number, the third number is a bug fix number. And that's a very simple numbering scheme. The problem is maintaining it and remembering to update the bug fix release number every time you kind of make any change at all. That's very hard to do. It's almost impossible to do manually. So in our build system, we're going to introduce a little bit of automation to this. Okay? So here's what our release numbering looks like. We have a major minor timestamp version number, where major continues to refer to the major release number, minor refers to a minor release number, but then following that we have a timestamp, year, month, day, hour, minute, all separated by dots, and that's basically the bug fix number or portion of the version number. The nice thing about this is that you can still kind of manually maintain the major release number and the minor release number, but if you are just making little bug fixes, which is what you do 80% of the time, then you don't have to remember to kind of increment that bug fix number every time. Instead, you're going to get a version of the system, you'll create a distribution, and the timestamp will indicate both when the system was created and that its sequence or its the sequence of bug fixes that were applied. Now the problem with this is that now you no longer, the nice thing about this is that you won't have two releases with the same bug fix number, okay, which is never good, or with the same version number. It avoids that problem, but it does not. The cost of it is that you've got this very long string of numbers that create the entire version number. So it's a trade-off, and for this class, I think you're going to be happy that you aren't constantly trying to update that bug fix number. So even though I said at the beginning of this lecture that it's important to allow different people to use different IDEs, at the same time you want to support any IDEs that you want to include in it in your development practices. We don't want to prevent people from being able to easily use Eclipse. So it's totally fine to actually include files associated with a specific IDE in your package, as long as you don't end up requiring an IDE in order to do things like build or test the system. So in Eclipse, to define a project, you need this file called .class, and you need another file called .project. And so we'll include those files in the distributions that we create with our systems, so that other people who happen to be using Eclipse can easily import the projects that we create and see them in Eclipse. Okay, so from now on, you'll be creating systems that will conform to the standards that are being kind of exemplified by this robocode-pmj-dacruzer file. And also you'll find that you can use this system pretty easily as a template. And I have precise instructions elsewhere, but the basic idea is that you'll download a fresh copy of this system, and then you'll strip out the dacruzer stuff from it, and you'll add in your own system's stuff, and the result will be with relatively minimal changes, a new system which uses our build framework, and you get all the power of it without having to write a bunch of ant code yourself. Okay, in terms of integrating Ant with Eclipse, Eclipse has nice support for Ant. If you want to run our Ant targets from within Eclipse, you can do that. There's a couple little things you have to worry about, which is setting Ant home and making sure that Eclipse writes out to a bin directory versus the build directory, where you can play around with that. It's not very hard. This example PMJ robocode-dacruzer example is a good example, but it doesn't show everything that we'll be doing later on in the class. So we're not at this point trying to support subversion integration or web app development or other kinds of metrics and so forth. So this is the basis, but it will be extended further during the semester. So getting back to the 3 prime directives of software engineering, it turns out that Ant is a pretty nice solution for dealing with both users who need to install the system, so installers, as well as developers. Okay, so it's not necessarily the best way to deal with our regular user community, but for the installers and the developers of the system, it's very helpful, not a complete solution, but very helpful for getting us to our goal of satisfying the 2nd and 3rd prime directive. There's other ways we could deal with the installation approach, like using specific packages like install anywhere, but Ant works pretty good for that. Okay, thanks a lot, and I'll see you soon.